Given a function, graph its vertical stretch. Number one, we want to identify the value of a being the constant. And then we're going to multiply all range values by the constant a. Now, part 3, if a is greater than 1, then the graph is going to be vertically stretched by a factor of a. If a is in between 0 and 1, then the graph is going to be vertically compressed by a factor of a. Now, if a is less than 0, meaning being negative, the graph is either stretched or compressed and also reflected about the x-axis. For example 13, we want to graphing a vertical stretch. So a function p of t models the population of fruit flies. The graph is shown in figure 20. So if we look at the graph here, we can see that we have an ordered pair at 0, 1. We have an ordered pair at 3, 3. We have an ordered pair at 6, 2. And we have an ordered pair at 7, 0. So a scientist is comparing this population to another population, Q, whose growth follows the same pattern but is twice as large. Sketch a graph of this population. So now we have to understand what this twice means. So because the population is always twice as large, the new population's output values are always twice the original function's output values. So graphically, this is going to be shown in figure 21. Now, if we choose 4 reference points, which we had already discussed here, 0, 1, 3, 3, 6, 2, and 7, 0, we're going to multiply all of the outputs by 2 since we're, again, multiplying it by twice as large. Now, twice as large, okay, comes back up to number 3. We can see that that number is 2, which is greater than 1. So, therefore, the graph is going to be stretched by that factor of 2. So, what we're going to do is we're going to multiply the outputs by a factor of 2. Again, since 2 is greater than 1, then it is a vertical stretch. So we have our original ordered pairs, and we're going to take our number 2 and multiply it by the outputs. So we have 0 and 2 times 1, which gives us 0, 2. 3, and then 2 times 3 gives us 3 and 6. 6 and 2 times 2, which gives us 6 and 4. And 7, and then 2 times 0, which gives us 7, 0. So now if we look at this graph now, you can see that now we vertically stretched the graph and went from 0, 1 to 0, 2, right? Because if we take a look at the original points, and I'll plot those points so you can see, okay, the original point was 0, 1, and so we multiplied the output by 2. Okay, the original point was 3, 3. The original point was 6, 2. And the original point was 7, 0. So you can see that this is what the original function looked like. And so that means that we have a vertical stretch by a factor meaning that you multiplied the function by 2. That means at the output. So symbolically, okay, the relationship would be the following. We had the original function q of t. Well, our new function q of t is going to equal 2 times the function. So this means that for any input t, the value of the function q is twice the value of the function p. Notice that the effect on the graph is a vertical stretch of the graph, where every point doubles its distance from the horizontal axis. The input values, t, stay the same, while the output values are twice as large as before.